Up to this point, we have discussed the architecture, use cases, and technology components. In this section, we will discuss the common network design practices in deployment. For high availability and redundancy, Viptela components are deployed in redundant active-active mode. This is true for the control plane and data plane elements, namely vBond, vSmart, and vEdges. The vManage NMS system is deployed in an active/cold standby for disaster recovery. For scalability, Viptela solution provides a scale-out model where the scale of the solution is not limited by scale limitation of a given element. Solution can scale out by adding additional elements. The data, control, management scale can be scaled independent of each other. Upon completing this module, you should be able to 1. Understand that SD-WAN solution is applicable and is deployed to small, medium, and large enterprises across all verticals. 2. Most common designs and deployments are simple. 3. Ensure you are able to whiteboard different designs at a high level. And finally, recognize that it makes sense to reach out to a TME until more comprehensive documentation is available. The Viptela control plane deployment is very flexible and can be deployed in public or private cloud hosted by Viptela, a managed service provider, or on-prem by the end customer in their data centers. Most commonly deployed model is to host controllers in Viptela's public cloud. For redundancy and high availability, two different regions are used in AWS. One set of controllers are deployed in one region, and the other set is deployed in the other region. vBond and vSmart are deployed in active-active mode across the regions. vManage is deployed as active in one region and is deployed in a cold standby mode in the other region. The backup vManage is manually brought up in DR situations where the primary active vManage is down and cannot be recovered. IP addresses assigned to the interfaces are private IP addresses from the RFC 1918 range, and AWS provides one-to-one NAT translations to public IPs for all the controllers. Control plane is established across controllers and the remote vEdges on the public internet. This model also supports data plane connectivity between the vEdges on other transports including MPLS, leased line, Metro Ethernet, and others. This means we can establish IPsec tunnels on other transports even when we have control plane on just the public internet. Customers like the simplicity as VM management of the controllers is done by Viptela, and the customer simply has to be concerned about overlay network operations. Some customers require a control plane connection over multiple transports. They want to have transport redundancy for their control plane deployment, for example, on Internet and MPLS. The SD-WAN fabric offers a flexible control plane where it can be extended to multiple transports as needed. One of the most commonly deployed designs is shown in the diagram above. This control plane design is usually seen in large enterprises in their data centers or by managed service providers for their end customers. The same high availability and resiliency principles apply where two data centers or regions are picked in different fault domains. A set of controllers is deployed in each. Public IPs are assigned to the controllers. These IPs are reachable from the internet through the DMZ or firewall, within the enterprise, or within the MSP's cloud environment. These public IPs are advertised into the MPLS domain as well. As a result, the same controllers are reachable from the vEdges over MPLS. For certain customers, they want transport redundancy for their control plane, but at the same time have to meet certain security requirements. In many cases, their security policy does not allow any direct communication to a publicly assigned address on MPLS. No communication will be allowed on MPLS destined towards a public IP through the data center. In this case, the controllers are deployed using private IPs and are advertised using those to the MPLS transport. As a result, the controllers are reachable via their private IPs. The traffic for the Internet domain is routed through the DMZ security stack in the data centers. At the same time, the traffic is NATed to a public IP before leaving the data centers. As a result, the controllers are available on MPLS via the private addresses, but on the Internet they will be reachable via public addresses. In this particular model, the V-bond cannot sit behind a port address translation or PAT type NAT. It can, however, sit behind a one-to-one NAT. No such restriction applies to the vSmart or vManage appliances. For this type of design model, it is strongly recommended to use one-to-one NAT type configuration for all the controllers. In the cases where the controllers are accessible via MPLS, it is simple to provide access to the data center hosted services to the controllers such as TechX, Radius, SNMP servers, and syslog servers. This is not as simple when the controllers are deployed in a public cloud infrastructure. There is a standard design where a software vEdge or a vEdge cloud is deployed along with the controllers in the cloud. The vEdges become part of the overlay, and the network management interfaces of the controllers are placed in a management VPN on the vEdge cloud. This provides secure communication between the controllers and the services hosted in the data center. The enterprise may implement policies that only allow users on the corporate network to access the controllers, and for authentication and authorization to go through the enterprise-hosted TechX or Radius systems. This provides the enterprise full control and visibility on services and users for the control plane. There are several approaches to migrating customers from legacy WAN to SD-WAN. The most commonly used migration strategy is highlighted in the diagram. Step 1. Identify the gateway or data center sites that will provide the bridge between the SD-WAN domain and the legacy WAN domain. Step 2. Deploy the vEdge in the gateway or data center location with a layer 3 peering with the existing routers providing connectivity to the legacy sites. At this location, we will run BGP or OSPF to exchange the routing information between the legacy and SD-WAN domain. Step 3. Start replacing the legacy routers in remote locations with the SD-WAN functionality on the vEdge routers. Step 4. During the migration, traffic between the SD-WAN sites will go directly from site to site, whereas traffic going from a SD-WAN site to a legacy site will be routed through the gateway or data center location. And finally, once the migration is complete, the legacy routers can be removed from the environment. There is support for a wide range of topologies for site deployments, including terminating multiple transports on a single vEdge. The vEdges can support up to 7 transport interfaces. With multiple vEdges, we can also support U-shaped topologies where different transports can be present on different vEdges. The transport connections are extended between the edge routers via a direct link between them. In such topologies, both the vEdges have access and visibility on all the transports. This capability is called T-lock extension and is represented by the topology in the top right corner. The vEdges can also operate behind a legacy router or can replace the existing legacy CE device. Standard mechanisms are also available on the LAN side, including VRRP, OSPF, and BGP. In this example, we have a small enterprise customer with less than 100 sites with 2 data centers. The sites are located around the United States. The controllers are hosted in the public cloud infrastructure. In the data centers, they have 2 MPLS circuits and 1 broadband circuit. In the branches, they have 1 MPLS and 1 broadband circuit. They utilize a local internet exit from the branches where they back up to the data center over MPLS for their SaaS applications. A single VPN segment is used in this topology. In this example, we have a medium-sized enterprise with 300 plus sites with a global presence and 3 data centers. The controllers are hosted in the cloud. This network utilizes 6 VPN segments representing 6 business entities across the WAN. Data centers have dual MPLS and dual broadband connections. The traffic flow again employs a local internet exit in the branches with a fallback to the data centers over MPLS. This diagram represents a large-scale global enterprise deployment with multiple data centers for North America and regional data centers in Europe and Asia Pacific. Controllers are hosted once again in the public cloud infrastructure. A wide range of access technologies, including DSL, cable, LTE, and MPLS, are employed in this environment. This network employs application-aware and performance-based path selection policies, regional aggregation and regional preferences for the data centers, and multiple VPN segments for the different business units. In this module, you learn that the controllers are flexible and can be deployed in public or private clouds, as a service, through managed service providers, or by the customers themselves. The solution supports small, medium, and large customers with diverse transports. This concludes the SD-WAN high-level network design and deployment module. Thank you for watching.